right, friends and neighbors, welcome back. We are doing Chapter 10 of the CCNA Volume 2, Network Address Translation. Something we all do. It's everywhere. Off we go. In this video, we'll have our key topics. The exam section is IP address scalability. We'll find out that, hey, we just don't have enough. We're going to, of course, cover the NAT concepts and their configuration. So the subsection here is IP services. Configure and verify inside source NAT using static and pools. Now, static and pools are two flavors of NAT. There's also overloading, or what we call dynamic NAT. So we'll start with static NAT, and then we'll do dynamic NAT. And of course, usually what you're doing is translating from inside to outside, and so we'll call this inside source NAT, which translates addresses to an outside address on the global or public address space, typically anyway. And we'll finish off with the do I know this already questions. So there are several ideas that go along with NAT, and one of them is private address network numbers. So there's two parts to this. There's the NAT or the translator itself, and then there's private addresses. And then, of course, there's the whole reason why we had to do this in the first place. So we'll get the basic idea, the main concept behind translating of private addresses to globally unique addresses. That is, addresses that are on the public internet. And I'll show you, a typical diagram that shows how the translation is done. And we'll go over the basic terms that we need to understand to really get our hands wrapped around what NAT is doing. And we'll also talk a little bit about the difference between static and dynamic NAT, which turns into PAT, depending on how we set this up. And we'll wrap it all up with a demo. So the fundamental idea behind all this is that address space is limited, right? At some point, we went to the box and the box of addresses was empty. So it used to be that you could call up IANA and you could say, hey, listen, I need an address space. Oh, really? How much do you need? Well, I need a Class A or a Class B or a Class C. And IANA said, sure, sounds good. But as early as the 1990s, and remember that all of our main RFCs come from the mid-1980s. So it didn't take long before the internet caught on and there were concerns that we might run out of space. And the 32-bit address space that we have for IPv4 addresses is really the problem. If we take that idea, what folks started doing is going, all right, what are we going to do about this? And there were two real solutions that popped up there. There was the short-term solution, network address translation, and then there was a long-term solution, IP version 6. But in addition to that, the classful system, right? Class A, Class B, Class C addressing was also very, very wasteful. And so RFC 4632 said, maybe we ought to break out of this class-full system and work instead with a classless system. And so that was the idea, that you could manipulate the mask to more closely specify the address space that you actually needed. So if you think about it, somebody says, well, I want a Class B network and I have 2,000 nodes. Well, if you're going to do a Class B network with 2,000 nodes, you actually were wasting 63,000 addresses. And so maybe it'd be better if we could carve off a space that was for your 2,000 addresses instead. What RFC 4632 said was, let's do just that. So we're going to be more efficient in our assignment of addresses. But addressing the depletion problem, or the more efficient use, was only part of what RFC 4632 was about. The other problem was that as more and more networks were joined to the internet, the routing tables on the core routers began to grow. Today, we're approaching 1 million routes on the core internet routers. Imagine what a router has to do to find the destination if it's got to search through 1 million entries all the time. Now, it's not exactly like that, but there's an awful lot of entries in a routing table. So the solution then, in addition to being able to manipulate the mask to be a more efficient address space, what we could do now is aggregate routing table entries. So you could collapse contiguous address space into a smaller number of routes in core routing tables. And so that became a very handy way to make processing of internet routing tables more efficient. So a little more detail on these problems, right? Address space, the classful system again was very inefficient. This example includes a class C and a class B. And if we compare those two, right, a class B has 65,536 possible, 65,534 usable host addresses, while a class C has 256 possible, 254 usable addresses. But what if you're somewhere in between, right? There was no way to match that up. And the core internet router problem, as I just talked about, now core internet routers all over the place have exceeded 500,000, with some of them coming up on 1 million, as I was saying. So with a router's limited memory and packet processing capability, right? One of the fundamental measurements we have for a router is the packets per second that it can process. Imagine if your routing table is enormous like that, your packet per second processing, boy, say that 3 times fast, goes down because you have so much to search for. And then on top of all of that, right, we still have the fact that we're running out of addresses. Somebody calls up and says, hey, I need more address space. There wasn't any available. So IANA officially ran out of address space in 2011, and ARIN, the North American Regional Internet Registry, officially ran out in 2015. So 10 years ago, we were actually out of addresses. And just as a reminder how addresses get to us, IANA is responsible for the entirety of the global address space. In fact, it's not just for IPv4, but also IPv6 and our port numbers and autonomous system numbers. IANA gives out chunks of address space to the regional internet registries. And you can see those if you go back to one of the old videos or just go out to the IANA site, you can see that. And then the regional internet registries give that to the internet service providers, and then they send those down to customers. And that space will be based on their clever manipulation of the address space using CIDR. So if you really want to understand this issue, the key RFCs to pay attention to would be RFC 4632 that describes the need for mask manipulation and to move away from the classful system. So really good introduction in that RFC can be found. And then the idea of network address translation is RFC 3022. So 3022 describes how NAT works, but RFC 1918 is where we find the private addresses that are allocated for use with NAT. Now, another way of thinking about this is that you could do network address translation and not be using private addresses. That's absolutely true. You can translate one set of public addresses to another set of public addresses. So there's the idea of the translator itself and then the private addresses. Now, the whole point of using private addresses is because we're not using public address space. We're not asking for more of the already depleted address space for the public internet. Now, RFC 1918 private addressing, it's a really interesting topic, not just because of the address space allocation, but we have to remember that if you decide, well, we need more address space, but we can't get it, so we're going to switch to private addressing, there's an evolution that has to go on, right? You have to say, I'm going to renumber all of my nodes, but I'm also going to have to figure out what I'm going to do about DNS. Anything that was publicly available via DNS will no longer be publicly available, or at least not accessible via public DNS because you're using private addressing. And folks all over the globe could be using the exact same addresses that you are. So moving a host from public to private or private to public involves not only a change of address space, but updating or modifying the appropriate DNS entries. And so without a little bit of work, you cannot get access to private hosts that are sitting behind a NAT box. And we have our 3 blocks here. The way to remember this, at least for me, is that there's a class A, B, and C size address space. And so a carve out from the class A is the 10 network. The entirety of the 10 network is a private address space. It's got a lot of addresses, so a lot of folks use this addressing because they're not constrained in any way, shape, or form. They can do whatever they want because it's such an enormous address space. The Class B block is 172.16, 0.0 to 172.31, 255, 255. So it's not everything in the 172 address space, 172.16 to 31. And the Class C block is 192, 168, period. But it's a good sized chunk. So anything 192, 168. So it's actually kind of a Class B size chunk of address space, but numerically it's carved out of the Class C. So how does this work? Well, for internally generated transmission, so this would be right here. So we've got this network. You can see it's the 10 net, and it is what we're going to call the inside. And so the NAT box on the edge here says, well, I'm going to translate. That is, I'm going to take any address or any packet that has originated on the inside network, so heading to the internet. There's an address or set of addresses right on the outside here that are public, and I'm going to convert all of these IP addresses here to the addresses that are being used on the outside. Now, we can do this a couple of ways. We can say, well, I'm going to do a static. So for every single address on the inside, I'm going to have a single address on the public side. Now, if you have a couple of nodes that need translation, that works out just fine. But if you have a whole bunch of nodes, maybe it's time to move something to a larger address space, like a pool, to where we have a larger collection of addresses. We define a pool, and the router just picks an available address from the pool. Now, the next step, if you've got way too much to worry about, you might do something called overloading. And that's sort of where we move from network address translation and specifying the addresses that we're going to use to port address translation, where we're just going to let the router figure out what ports are available. And so if I had 1,000 nodes on the inside here, I might just simply say, well, we're going to do overloading on the outside. Okay, so those are our flavors of NAT, right? Static, one-to-one. It's not a whole lot of conservation of space. The only benefit is that I get to use private addresses on the inside, pools, and then overloading. Now here is what a translation table looks like. So if we take a look at, say, 1.2 here, sending traffic out. Here is the IP address and port combination. And I'm talking to somebody on the outside internet. The address that I choose is one right here. So on the outside, the destination believes that it's communicating with this node right here. So the transmission comes back, and the NAT box says, well, I have a table that describes where I came from on the inside. And so on the way back in, the NAT box, the router that's running NAT, just converts it right back to the original value. Now here's a configuration example. So in this case, I've got a couple of interfaces. In this case, I give it an IP address here. This one maybe on the outside, on the public side, maybe connected to my ISP, gets a DHCP-based address. I define one interface as being inside and one interface as being outside. So here I've said IPNAT inside, and here I've said IPNAT outside. Now the next thing would be to decide how I'm going to do my network address translation. In the case of a pool or a static, I would say, here is my actual mapping from my inside addresses to my outside. In the case of overloading, what I might actually do is say, well, anybody that matches this access list will actually be translated, and I might have a statement like this: IPNAT inside source list. So if you match the source list, go ahead and translate on interface G0/1, where G0/1 or the outside is the address that you're going to use. Now, if you're going to verify this or see what's happening, right, we have a couple of commands to use. We can do show IPNAT translations or show IPNAT statistics. And sometimes that list gets pretty big if we're doing a lot of traffic, so you can clear it out and then watch what's happening at any one particular time. Now, there are a couple of things that can go wrong with this, right? The chapter has a whole bunch of things that can go wrong with this, but a very common problem is to switch up the interface assignment. So it's very easy to confuse inside with outside. And it's also easy to pick the wrong address in statements such as this. Now, another question that comes up is, well, what happens if I don't match the ACL, right? What happens if I'm going to translate based on this ACL and I don't match that ACL? Well, the answer there is that you're simply routed and not translated. And we'll see if we can do that in the demo too. All right, so off we go. Let's get a demo set up, and we'll do a couple of versions of NAT. All right, I have a small routed topology set up here, a couple of nodes. So on this side, we see that we have the 172.16.0.0 network, and so that'll be my private address space. And then we have the 129.21.0.0 address space. That's public, happens to correspond to RIT. Here is my current routing table. So there we have it, just a couple of networks set up, and we're not doing anything in the way of NAT yet. And just for fun, we can see that pings work. All right, now, in a ping to the outside, we're going to call this sort of the inside, right? And this will be the outside. So in a ping to the outside, right now we're just straight up routing. So what that looks like when it gets to the outside is we can see, hopefully you can see this, that my source IP address is 172.16.0.1 and 129.21.21.1. So there's no translation. I'm just doing routing. Well, let's start configuring our network address translation. And initially, we'll do static mapping. So I'm going to say interface f0/0. And commands that I have available, we'll do IP NAT. There's really not too much to do here. But this is going to be my inside interface. And then I'm going to do IP NAT outside in F0/1. Well, the next thing to do is figure out what my translation is going to look like. So what I'm going to do is, first of all, we'll say, well, what are my options here? Now, we're calling this, right? The chapter calls it inside address translation. So that's what we're doing. So we're going to say inside. Well, what am I going to do? Well, I'm going to translate source IP addresses to something based on some rule that I set up. Since I'm not doing an access list yet, we'll say our source. So I'm going to do a static mapping to begin with. And what I'm going to do is specify that the inside address is going to be translated to a particular address on the outside interface. So what I'm going to say is we will translate 172.16.0.1. Well, what am I going to translate it to? Some global address on the outside interface. So since we know that's the 129.21.21 address space, let's make it recognizable. We'll make it 99. If I ping from the node that doesn't have anything to do with the translation, oops, I suppose we ought to ping the right one. We're going to go to the outside. Well, what does that look like on the outside? Well, this will be exactly like we saw earlier with the addresses being visible. So here we can see 172.16.0.2 going to 129.21.21.1. What happens if we ping from the node that's being translated? Now we've already pinged this node, but now we've got some translation statements in there. Well, here goes our message to the outside. And now we can see that we've got this source IP address of 129.21.21.99. That is the static assignment that we made. And we're translating to our outside address. And we're still communicating with this outside address 129.21.1. Now, who does the 129.21.1 or 129.21.21.1 think that it's communicating with? Well, let's see what the return is. Well, let's see, coming back from 129.21.21.1, it believes that it's communicating with 129.21.21.99, right? So 99 doesn't really exist, it's just the static translation, but it comes back to this interface And now what does that interface do? Well, it forwards it on to the originating node. And a really good question at this point is, how did that work? If we were using a completely different set of IP addresses, how did this work? And the answer is in the translation table. So on my router, I have a translation table that describes all of this mapping. All right, so what do we have here? The inside global address is the one that we are assigning to the traffic that's going out. Here is the inside local, the original IP address. And here is the original target in our communication. So both for the outside local and the outside global, this is the node to whom we are talking. Now, this is ICMP traffic. So these are not actually port numbers. These are numbers that are pulled from the ICMP header. But let's see what happens if we actually do an application. So I am now going to use the traffic generator in Packet Tracer to send traffic going out there. And since we're doing HTTPS, we'll just start at port 80. Well, actually, this is the inside, so we'll do, I don't know, 2000. Make it easy to find. And we'll do periodic. All right, so what we're going to do from our inside host now is we're going to say, I'm going to send TCP-based traffic on the way out. So here we go. And we should be able to see the TCP traffic going. Now it's just the generator, but what does this look like now in the translation table? Well, here we can see that it's now TCP. There is the original port that I started with, and of course we're going to port 80. Now what we're seeing here, unlike the graphic that I showed you earlier, is the entirety of the translation table. So the transmission goes out, it starts off going to this particular endpoint, and then we do the translation. So when the transmission comes back, the outside node, right, 129.21.21.1, believes that it's communicating with 99. And what 99, or the router, actually does is it says, all right, who was I communicating with? What should this be remapped to? So that's the entirety of the translation table. Now, the translation table is also sometimes called a matched pair of matched pairs because the source and destination IP addresses and ports all go together so that we can not only translate on the way out, but translate on the way back in. Now, we can also take a look at the statistics for our translations, and we see that there's some traffic that's been translated and some has been just routed through. And of course, we know that because I wasn't translating everybody. Well, what if we were to use overloading? What if I didn't want to specify a particular address on the outside? If I just said, well, I'm going to let the router figure it out. So instead of specifying that I wanted to use 99, I'm going to remove that command and add an ACL instead and then let the router figure it out. So this command will allow me just to remove that. And now what I'm going to do, I could use a pool, but if I want to let the router just figure it out, the next step is to say, let's do protocol address translation, and we'll just say, well, we're going to overload. So what I'm going to do first is an access list. So I'll do access list 10, permit. Now, because we have two nodes here, I could write an ACL that applies to both of them. But I'm going to write a very specific ACL so that we can see what happens if we don't match the ACL. So I'm going to say permit 172.16, and we'll do the other host this time. And that's it. We'll just leave it right there. So now I'm going to say, let's make a NAT statement that utilizes this particular access list. So I'm going to say IPNAT inside source, again, source translation, source list 10, right? And then what do we want to do? Well, now we want to specify which interface we're going to use for the translation. So our interface that's on the outside will be interface F0/1, and then we'll say overload. All right. So just as a review, we'll take a look at our configuration, right? We have the 16 and that it's inside, and we have the 129.21 that is outside. But the only other statement that we have right now is we have our NAT statement and, of course, our access list. Well, let's see what happens when we do transmissions now. Well, before we do that, I suppose I should clear IPNAT translations, because otherwise my router will continue to try to translate based on the translation table. Okay, so our translations are gone. Let's take another look. All right, first we'll track the ICMP traffic. So we can see that on the outside, our ICMP traffic appears to have come from .254. So we're not using the static mapping, we're just saying to the router, look, figure this out. And if we just tell it overload, it'll use its IP address and try to do all the protocol address translation right there. But what about that TCP traffic? Well, the TCP traffic, because I changed the translation, is now back to 172.16.01 on the outside. This says a couple of things. One is that if we clear the translations, we can change things on the fly. And the other one is that if I don't match the ACL, I'm just going to be routed, not translated. I'm not going to be denied. I'm going to be routed and not translated. So this is a different use of the ACLs. All right, I think that'll about do it for our demo. All right, do you know this already? Questions? Which of the following summarized subnets represents routes that could have been created for CIDR's goal to reduce the size of the internet routing tables? Well, there was just one answer there. That was the 210.0.0 network. And the reason for that is because this is a mask that aggregates. The other ones did not have a mask that aggregated. Question number 2, which of the following are not private addresses according to RFC 1918? B and E, 172.33 is outside that range, right? 172.31 would be the top, and then 191 is not in the address pool for the Class C section either. With static NAT performing translation for inside addresses only, what causes NAT table entries to be created? All right, so when you're doing static, which is what we did with the one-to-one mapping, the minute you have that, the translation is in the table automatically. With dynamic NAT performing the translation for inside addresses only, what causes the NAT table entries to be created? Well, since we're creating it on the fly, right, dynamic, we don't know what the traffic is going to be, so we have to see packets first. Question number 5, NAT has been configured to translate source addresses of packets for the inside part of the network. Makes sense. But only for some hosts as identified by an access control list, which of the following commands indirectly identifies the host? Well, if you take a look at your access list, you'll get an idea for who is being translated. All right, question number 6, examine the following configuration commands, right? So here is an interface that's been given an IP address. It is the inside, and here is another interface that's been given an address and no designation of being outside. And then we've got our NAT command and then our access list. If the configuration was intended to enable source NAT overload, which of the following commands could be useful to complete the configuration? So in other words, what's missing? We needed 2 things here. And one answer was that we needed to do the outside, the NAT, IPNAT outside. So we got IPNAT inside, but not IPNAT outside. And then if we're doing dynamic NAT with this access list, then we could use overload right here. And our last question, number 7, examine the following show command output of a router configured for dynamic NAT, right? So this would have been show IPNAT statistics. Users are complaining about not being able to reach the internet. Which of the following is most likely the cause? Now, what we have to realize is that if you're doing network address translation, it's a problem for folks that are not being translated because they're using private addressing. And the outside internet would not know how to get back to those addresses. And so when we've got a whole bunch of misses, like this here, that means that the access list that we're using is not translating everybody. So that also means that the pool is not big enough to handle all of the addresses. So in other words, we've got this pool and access list combined that says I'm going to provide translation for a certain number of addresses. So in this case, the pool is not large enough. All right, what's on the horizon for Chapter 11? So this is sort of next level stuff, quality of service and per hop behaviors. It turns out that you can tell a router how to handle traffic with policies, and we're going to take a look at that. So a key set of ideas, managing bandwidth, delay, jitter, and packet loss. And the fun rhyme for the day, COS, QoS, and TOS. And then finally, what we use today is the Differentiated Services Code Point Field, or DSCP. All right, well, we've been doing static and dynamic NAT in this particular video, the key RFCs. 4632, 3022, and 1918 for our space, our translation, and our addresses. And if you were going to read an RFC that's probably one of the most impactful that we have for how we do things today, I think 4632 ranks right up there. Of course, we talked about static versus dynamic NAT, and we've got a couple of flavors of NAT, one-to-one mapping, that's the static, pools, and overload. Well, there we go. Like and subscribe to experience quality of service in the next video. May those packets always reach their destination, no matter what kind of NAT you do. And hey, this is CCNA. We're doing NAT. We're about to do QoS. You can do this.